Okay, right. Hi everyone, thanks for coming. The final session today is session 6 on effect sizes, type 1 or type 2 error. That doesn't mean type half error, that's type 1 or type 2 error. And it's on statistical power, what is that, and power calculations. So we'll briefly cover this. First of all, why do we even need to do power calculations? Now, this is more relevant for when you're like writing grants and such. Like, essentially, the point of the power calculation essentially answers this question: how many animals or how many subjects do we need for this experiment? And why is that important? Well, let's pose the question: what if we have an underpowered study? What does a small study, small sample size? What do the results mean? Well, let's just say if it's significant. If your results are significant, what could it mean? It could mean that you have a sampling error. What does that mean? I'll explain that in a second. So that's a type 1 error. When you have a sampling error, it's basically saying you may have a group, the results that you see are just because the people or subjects or animals you collected just happen to be outliers already. And so it's just by chance that you got a significant result. And so that's actually not good. You don't want to discover something by mistake. So if it was significant, that could be bad. Or what else could it mean? You could have a bigger effect size than expected. And I'll explain that shortly. So if you were thinking that, for example, males and females, let's say males, you thought that they were on average 10 centimeters taller than females, but you only took like an average of 3 people versus 3 males versus 3 females, and then you actually still got significance. Maybe instead, the effect size, maybe they actually should be like 20 centimeters on average or taller. So what you expected was wrong, and you actually should have found, you should have been expecting a bigger effect size. That's not necessarily a bad thing, but it just means that with a small sample size, you can see if you get a significant result, what's the probability? Is it likely that you just have outliers, or is it because you should be expecting a bigger result or a bigger difference than expected? Chances are it's probably going to be a sampling error, provided if you have only a small sample size or an underpowered study. However, what if you get not significant? What if you get the result not significant? On one hand, if you found that your data, if your results were not significant, what you might have done, because it's underpowered, you have a small sample size, you could have committed a type 2 error. And I'll explain what type 2 error is on the next page. Or you could be, you should be expecting a smaller effect size than expected. So for example, like I said, if males and females, let's say the true effect size, the true difference is like 10 centimeters taller, but you are expecting 20 or something. However, and you got not a significant, you were planning an experiment based on the idea that you thought there were 20 centimeters taller than females, men were 20 centimeters taller, and you got a not significant effect size, a not significant result. It could mean that the true effect is actually smaller than expected, i.e. 10, or you've committed a type 2 error. So just recall that, errors, they are errors, and errors are never a good thing, generally speaking. And so we'll talk about effect size shortly. But I want to finish this thought. What if you have an overpowered study? Well, if it's significant, if it's statistically significant, then it's wasted resources. And if it's not significant, then there's probably no true effect. Probably no true effect. So let's say, again, similar example, if you had, if you wanted to test the hypothesis, does drug X reduce blood pressure? And you recruited 1 million people, you gave 1 million people drug X, and you found, well, yeah, it does. And it's an overpowered study. It just means that you've wasted resources by recruiting way more people than necessary. And if it was not significant, well, then you'd be pretty confident that their drug X does not reduce blood pressure. And yeah, so that does tell you something new and does contribute to the literature, but obviously you don't want to waste resources. So it's all about balancing whether you want, you just need the perfectly just right sample size. And that's what power calculations do. That's what they aim to do. So let's have a brief definition time for defining type 1 and type 2 errors. Now, I've already touched on type 1 error. Type 1 error is the probability of detecting a difference. Sorry, a type 1 error is when you detect a difference when no true difference exists. So let's say the height of PhD students versus the height of master's students. If you detected a difference there's no good reason why they might be different, and the null hypothesis might actually be true, that there is no difference in height between master's students and PhD students, but you still detected something, a difference, and therefore that's a false positive, and that's why we call it an error. So if the truth was that there was no difference, and yet you still detected a difference, a positive significant test, then that would be a type 1 error. And we'd call that alpha. Alpha is the type, and that's the next line over here, type 1 error rate, the probability of making a type 1 error. And recall that probabilities exist between 0 and 1. And we typically just arbitrarily and perhaps, quite arbitrarily, we say alpha typically is restricted to 0.05. So if you found that the probability, given the null hypothesis, the probability of seeing seeing the values that you saw was less than 0.05, then you call it significant. And however, you never know what the truth is. You just get the p-values. However, if the truth is that there is no difference and you get a non-significant test, have you done an error? Have you committed an error there? Obviously not. So that's great. We're happy. That's good. We don't want to commit errors. Now, what about a type 2 error? Well, type 2 errors are detecting no difference when a true difference exists. So let's say the height of high school students versus the height of PhD students. Maybe for some reason, maybe PhD students are taller because they're adults, whereas high school students, depending on what age they're, and they just might be shorter. Now, there might be a very subtle difference because typically high school students, they should be adults by now, but well, around the height of adults. But you might need, there might be a very subtle difference. And so whilst the truth is that there is a difference, let's say you only get 5 high school students and 5 PhD students and compare the difference. And if the truth is that there is a difference and you got a statistically significant effect, you haven't committed an error, right? That's good, you found the truth. However, if the truth is there is a difference, but you found a non-significant test, like I was saying, if you only got a few things, that's what we call a type 2 error. And I'll put in brackets beta. And that's what's written up here. Type 2 error is detecting no difference when a true difference exists. And type 2 error rate, beta, is the probability of making a type 2 error. Now, Type 1 errors are much more visible and much more obvious because when you do a t-test, you're given a p-value and you can determine 5% is the cutoff. However, with type 2 errors, recall that of all the things that we do, all the tests that we do, we always assume the null hypothesis. So for example, if I did a test, males versus female height, and we said males are taller than females, our null hypothesis is always, no, there is no difference in height. Whereas the alternative hypothesis is there is a difference. And we always do a t-test under the assumption that the null hypothesis is true. And so if we have p is greater than 0.05, let's say it's 0.2, then we say, the probability of observing our data is 20%, and that's pretty likely. So therefore, we don't have enough evidence to reject the null. Or if it's below 0.05, like 0.01, then we do have enough evidence to reject the null hypothesis. It's always centered around the baseline, the truth being that there is no difference. That's the whole premise behind frequentist statistics, which is all the statistics that we've been sort of doing. We haven't been talking about Bayesian statistics. And so that's why type 1 errors are much more visible, but type 2 errors are much more subtle because you never know what the truth is. Because we always assume that the truth is that there is no difference, and then we're finding something new, but it's just a different mode of thinking. Now I want to introduce another concept of statistical power, and statistical power is the probability of detecting a difference when a true difference exists. And it's, by definition, it's 1 minus beta. So if I'm just going to write here. By traditionally, when you write a grant proposal, you should be aiming for alpha equals 0.05 and beta equals 0.2. So therefore, 1 minus beta is 0.8. What does this? Oh, sorry, you can't even read that. So traditionally, we will always put alpha at 0.05, unless you're doing some genome-wide association study, in which case alpha is like it's like 1 e negative something. It's very, very small. And physics, I think, does like 5 sigma, meaning 5 standard deviations away or something. So like p is like 0.00000000001 or something. However, in biomedical sciences, we typically just say alpha, we set it at 0.05, beta is 0.2. What that means is the probability of a type 2 error being 20%. Otherwise, saying statistical power, i.e. the probability of detecting a difference when a true difference exists, we limit that at 80%. We typically aim for 80%. Now, let's say in the justice system, if someone genuinely, truthfully was actually guilty, and we said, we want to have 80% chance of detecting whether this person is truly guilty, you can see that that's sort of like, that's sort of the analogy, if the truth is that they are guilty, truth is they're not guilty, you can think like a type 2 error is when they are guilty, but they're let off scot-free. So 80%, so typically we only want that to happen 20% of the time, 80% of the time. Obviously in the justice system, sorry, that's a weird analogy, but that's a different sort of thing. The justice system is mostly based on not convicting an innocent person. But yeah, if that helps, being like, yeah. So the truth and what your test does are two different things. Okay, also want to introduce the concept of Cohen's d, or effect size. So Cohen's d is a standardized quantitative measure of magnitude of the experimental effect. And Cohen's d is equal to the mean of the second group minus the mean of the first group divided by standard deviation. I want you to think of it in terms of how many standard deviations away is that population from my population. So I don't know, let's say, okay, because I keep using it, males versus female height. Let's say the standard deviation, the average deviation from the mean is roughly 10 centimeters. On average, people deviate from the mean 10 centimeters. So let's say male height is roughly 180 centimeters plus or minus 10. And our standard deviation is 10. We want to see how many standard deviations away is female height from here. So what if I got a group of females and measured their height? If it was 160, that would represent 100 and male average height for a sample is 180. That's 180 minus 160, so 20 centimeters, divided by standard deviation, which let's say is 10. So that effect size would be 2. And what I want to illustrate is that Cohen, when he published this paper, basically he wrote, if you find an effect size of 0.2, that is a small effect size. If you find an effect size of 0.5, that is a medium effect size. If you find an effect size of 0.8 or above, that is a large effect size. So when we just found an effect size of 2, that's a massive effect size. So generally speaking, you need to know, whenever you do these calculations, you need to know your effect size in mind. And how do you do that? Well, you can back calculate it from other people's data, from preliminary results. So you can figure out what an effect size is, and then you should plug in the numbers alpha equals 0.05, power equals 0.8, and such like. And we'll go through some power calculations on the next page. But yeah, it's just introducing the effect of the concept of effect size and measuring basically it's how big relative to its standard deviation. So are there any units for effect size? No, because remember the mean, let's say it was height. Height is measured in centimeters and standard deviation is also centimeters. So units wise, it cancels out. Cohen's effect size does not have units. And that's the point, because it's a standardized measure. So yeah, and these are arbitrary numbers, granted, yes, they are arbitrary, but nonetheless, it's just kind of stuck in the literature. You can be like, oh, look, we found a significant result and the effect size was 0.5, and therefore that's a medium effect size. Obviously, depending on your field, it may be different, but yeah, that's just the guideline. So as I mentioned, you're going to come into problems with identifying prior effect sizes from prior literature. So first of all, you can either look for test statistics to convert them into effect size, or you can even manually compute them. So that is why in everything that I've done in this course, as I've always told you, please include your F statistics, your T statistics, because using those numbers, you can absolutely back calculate that and convert that into an effect size, a standardized thing. So, and also include your degrees of freedom and your N, because that is important. So for example, if you needed to change chi-squared into an effect size, you can simply plug in, you can use a library called compute.es, and you just use this function chi-es. Chi-squared is 5.44, n equals 60, and oh, look at that. It just punches out the D, the Cohen's D is 0.63, right? And so that's why it's really good practice to always include your test statistics, because that way you can back calculate it into an effect size. Hell, you could even write what your effect size is in your paper to help other people convert your results even more easily. T statistics, yep, very easy to convert into effect size as well. But note how T statistic, that's assuming if you have 2 independent samples. If you have 15 in group 1, 15 in group 2, you do need to note, you do need to include N1 equals 15, N2 equals 15, and then you also need to give the T statistic, and then yep, the D is 0.78, so that's verging on a large effect size. And 95 CI, 95% CI stands for 95% confidence interval. Yeah, and if you have an effect size of 0, what does that mean? It means that there's no difference. So the fact that the 95% confidence interval doesn't actually include 0 means that it's also a statistically significant effect size. Yeah. What about correlation? Again, if you did correlation, Pearson or Spearman's correlation, yep, you can use that to calculate an effect size. So R equals 0.85. If you had N equals 100, then your effect size is massive at 3.23. And proportions as well, if you had proportions, so 50% of my plus a control group received a stroke versus only 20% of my drug group received a stroke, that's proportions. You can absolutely do that. P1, 73% or 20%, and you had 50 in group A in the first group and 40 in the second group, or whatever. You know, there are ways you can always convert those all into that, or you can use that. You can use all of these numbers to convert it into an effect size, a standardized effect size. So that is one of the reasons why I've consistently reminded you to please always include test statistics. Now, if you come across a paper that does not include that, which is very annoying, and that has happened to me, you can use a ruler. Use a ruler, measure that out, and then measure that. So that hopefully they have also included the fact that error bars are standard error and not error bars are not standard deviation. It doesn't matter. As long as you need, what you will need to know is how many were in this group, n equals 6, and this was n equals 14, and then you'll need to know the error bars. So you could use this, do this in image J. I'd recommend doing it in image J rather than printing it out and using a ruler. Do we know how to convert this into, okay, I'm going to write some working and then on how I would do it. And yeah, so first of all, you measure the scale. I don't actually have a ruler with me. Do I? No. Okay, that's all right. I already pre-did this. So you measure the scale from 0 to 2.6, and I'll tell you now on here, it was 6.6 centimeters. And then you get the scale 6.6 centimeters divided by 2.6 being the units, and that was 2.53846 units per centimeter. And then you get the mean of x. So basically, all the point of this is trying to read out what number is this. I mean, right now from my eye, I can be like, oh, that looks like roughly 1.7, but you want to read out as exact a number, and that's why you get a ruler out and do it. So x, the mean of the control group, I measured it out to from 0 to there was roughly 4.35 centimeters. And so then you do 4.35 divided by 2.538 ... which is that's converter, and that gives it to be 1.71 units. 1.71 units. So you can be like, oh, okay, so that was exactly 1.71 units. Similarly, you get the mean of the drug group, and I measured that to be roughly 4.8 centimeters. And then, so what you do is you get 4.8 divided by the conversion, 2.538 ... and that gives me 1.89 units. And does that look plausible? Yeah, it's roughly around 1.89. Yeah, that seems plausible. So now I got the mean of the control group and mean of the drug group. Now, what else do I need to calculate effect size? I need the standard deviation. Great. Okay. So first of all, let's calculate the standard deviation of the control group. Now, first of all, actually, the error bar is a standard error, which is standard error of the mean. So let's just get to the standard error of the mean, the SEM of the control group. And when I measured that in the rule, it was only 0.1 centimeters. And if you divide 0.1 divided by 2.538 ... that's only 0.04 units. And if you do SEM of the drug group, that's also 0.1 centimeters, which is also 0.04 units. And now this is where you integrate knowledge from seminar 1, where I talked about what the equation for SEM was. See, the standard deviation is equal to square root of n times by SEM. So if your SEM was 0.04 and your n, let's say, of the drug group SD equals square root of 14 times the SEM, which was 0.04 units, your standard deviation would be roughly 0.149666 dot 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 dot. So then, now, technically speaking, because you have two standard deviation, you have two error bars, you're supposed to calculate a pooled, P-O-L-E-D, like a pooled, a combined standard deviation. And in order to do that, you're supposed to square this number and then times that by 14, because there are 14, there's a standard deviation of 14 people weighted in this, whereas there's only a standard deviation of 6. Where did I get 6? Because let's hopefully in the figure caption, they did tell you how many were in each group. But let's just take just the standard deviation of 1. You can take the standard deviation, if you want to be more conservative, you can just take the largest standard deviation, which would have been this one. Because if you think because both of the standard errors were 0.04. If you did square root of 6 times 0.04, that would be a smaller number. So I'm actually being a bit more conservative by taking just the standard deviation of the larger group. But anyway, now that I've got standard deviation and I've got the mean of control and mean of drug, I can now calculate Cohen's d, 1.89 minus 1.71 divided by 0.14966 dot dot dot, and that equals a Cohen's d of roughly 1.2. So I did these calculations beforehand, but that just kind of shows you. Yeah. Oh, sorry. Yeah, thank you. Sorry. Yeah, I did these calculations beforehand, but it just shows you the sort of stuff that you could do. And if you're familiar with ImageJ, yes, you could do it much more easily in Image. Well, not that much easier. It's the same process. You still just do it. But yeah, you can do that in ImageJ as well, or frankly, any image editing software like Photoshop. It's just a bit of arithmetic. And that's how you'd find a Cohen's d to inform your next grant proposal. Now, it's not just enough to know mean 1, mean 2, and standard deviation. I also wanted to raise the concept of the balance of groups. So let's move on to the next page. The balance of groups. Let's use a basic 2-sample t-test as an example. Let's say we have a total n of 100 people, and we want a desired effect size of 1 and alpha equals 0.05. Notice that we fixed n, we fixed a desired effect size, and we fixed alpha. And so you're now allowing power to vary. So you can see on the y-axis is statistical power, and on the x-axis is percentage of samples in control group. Where in this graph is power the largest? When the percentage is 50. When you have a 50-50 separation between control and drug group, that is when you will achieve the highest statistical power. But for various experimental reasons, you might not want to have 50-50, 50% in the control group, 50% in the placebo group, especially if you have like multiple groups, then it becomes even more complicated. So if you don't want that, you'll note that you'll have to be sacrificing statistical power. So that's just something to keep in the back of your mind, that whenever you do this, just make sure, like, in order to achieve the most power, you want 50% of your samples to be to belong to the control and 50% to the other. When you have even a balanced design, that's when you have most statistical power. So the next part is, so therefore, taking all this previous information into consideration, here are some steps for your power calculations. And I do put this, use at your own peril. I've never written a grant, so this isn't a tried and true method. So I'm not a research fellow, I'm a PhD student, so obviously no. So first of all, identify your desired type 1 error. Typically, for most of us, that would be 0.05. Identify your type 2 error. Again, for most of us, that would be 0.2. Therefore, if 0.2, type 2 error is 0.2, our statistical power is 0.8. Good. Then you need to identify your potential effect size to detect. So that will be based on prior research or going to a graph and doing this stupid calculation, or simply, just getting a test statistic and converting that. So once you've got type 1 error, type 2 error, get your effect size that you want, then identify your study design. Are you doing a between group study or are you doing a within group study? Whenever you do repeated measures designs, paired t-tests versus when you do independent samples t-tests. So if you do if you did a crossover study, so people received drug X, then they received placebo, or the other way around, that usually has higher statistical power than just getting two separate groups. And I'll talk about that in the following example. And then also, obviously, you need to identify practical or cost restrictions, and then you can perform your power calculations for various study designs. Right. Okay, I think I go through that later as well. So let's say, here's an example. You have developed a new drug called drug X and want to see if it can treat COVID-19. Drug X can reduce inflammatory biomarker concentrations within 1 day, which would hypothetically improve prognosis. 3 past studies investigating COVID-19 treatments found practical significance when effect sizes for reducing inflammatory biomarker concentrations were 0.73, 0.84, and 1.52. So there's evidence that you've looked at past research and found, okay, 0.73 is useful, 0.84 is useful, 1.52 is good. Given that you're applying to a major funder, you want to make this trial as big as possible with no money or resource restrictions. Assume that you want type 1 error rate to be 0.05 and type 2 error rate to be 0.2, such that power is 0.8. So identify what sample sizes you need with different study designs. Okay. Okay, I think this is where I need to change over, and let me just get, do I have a, so, I mean, that's the command you can run in R, because I believe R has a built-in statistical package, built-in power calculation package. And so I'm just going to switch over now. Switch over and switch that to that. And now I will do this. Okay, and I will hide video. Cool. Okay, so first of all, let's run this stuff. Okay, so this is going back to 6.3. We're not going to do that. We're going to just look at 6.6. 6.6. So just look at the notes when it refers to it. So I think identify what sample sizes you need with different study designs. So as I was saying, if you had a 2-sample study design, let's run that, you're going to need n equals 30.45 or 30.44807. So if you had 2 samples, you'd need n of 30.4. And note that n is number in each group. But if you just had a paired design, a crossover design, then you would only need 16.75. And remember, 16.75, that's 16.75 people you need, but they would receive the placebo and they would receive the drug. So, and that experimental design, is a practical consideration, because depending, like, some people might drop out of the trial, so it depends on how well you think you can retain participants and such like. So that's what I mean by paired tests having higher statistical power, because you can get away with having less people. And now the part 3, it says your study went well. You're applying for the next grant. You want to see if drug X can actually reduce the proportion of death. Currently, some studies have shown the death rate from COVID-19 is 0.1. You wish to cut the likelihood of death in half. Identify how large the sample size you need. And this is, so notice how in this command, I have left n equals null, meaning I don't know what n is. That's what I want R to spit out for me. I do know what my P1 is. P1 was 0.1, which is the death rate of COVID-19, and I want to cut it in half. I want to reduce it by half, which is to 0.05, and I know what statistical power I want, which is 0.8. And you simply run that, and let's see what we get. You need to recruit 434 patients, or 435. In order to meet it, you need to recruit 435, because, yeah. And note that that is n is number in each group. And this is assuming that you have a 50% balance in each group. If you wanted to make it a little bit more fancy, you need to use other tools to be able to do that, to be able to calculate unbalanced study designs. Great. Now 6.7 is talking about cost restrictions. You're writing a grant for your next set of experiments. Each experimental unit costs $200, but with a rough success rate of 0.95. In other words, 1 in 20 experimental units fail. This could range from just your samples not working, the machine not working, or something screwed up. That happens in science, as we all know. So as usual, you're expecting alpha is 0.05, power is 0.8. The effect size you're looking for is roughly in the 0.4 to 0.6 region. So that's a medium effect size, roughly. If you're allocating approximately $30,000 for experimental costs, what effect size can you detect using a 2 independent samples test? So now this is now a pilot study. We don't know what the effect size is, although we have a rough estimate of 0.4 to 0.6. I think I may have, no, I don't. Okay, never mind. So cost restrictions. So here's the effect size table. Here's a table of, okay, so I've put the D at 0.4 to 0.41 to 0.42 all the way to 0.6. And then I've created a for loop. So for I in sequence 1 to 21. Why did I say 1 to 21? Because there are 21 rows in here, and I is the iterative difference. It iterates through here. So this for loop identifies the corresponding n needed to achieve a given effect size. So if I run this, let's just put I equals 1. For those of us who aren't as familiar in coding, this is how I test for loops. So temp D is this, ES table, this. So what is ES table? ES table is this thing. And then when you do ES table D, it means you're taking this factor, and then you're taking this, the ith value, which is 0.4, because it's the first value. So temp D is 0.4, and then you just grab this, and then temp becomes this massive object. It's not that massive. And then you ES table question n. Okay, you can look at this in more detail, but essentially, if you run this for loop, it will give you something that's quite nice. ES table will give you all the n values of there. Basically, I'm running 21 power calculations to give me all the n values across here. That's essentially what that bunch of code is doing. Now, the fact is, you can't have 94.35 subjects, so that's why I use the next line, round the number up. You don't round the number down, because then technically you're making it underpowered. You'd rather be slightly overpowered than underpowered, so therefore we're ceiling it. Ceiling just means even if it's 99.08, I want you to make it go round up. So that's what it will do. And then I also want to divide it by a 95% success rate. Remember, 1 in 20 experiments fail. So therefore you want a bit of buffer for the money. So that's why you want to divide it by 0.95. And then again, round the number up again, because you can't have half of a number. And also recall that the N reflects the numbers per group. And so big N reflects the total number of samples. And then the cost, remember, it costs $200 for the consumables or whatever. And then that's all the calculations that I've done in here. And then simply, let's run a ggplot, and this should plot something nice. And you can see from D to 0.4 to 0.6, let's say, okay, sample size is on one axis, sample size. Notice how in order to change it from sample size into cost, you just multiply it by 200. So therefore, given this, what if, and if you only have a limited $30,000 you could apply for, what effect size will you be able to detect if you max out everything? If you max everything out, you just look at 30,000 come across and come down, you'd be able to detect an effect size of roughly in the region of 0.4748. So that's one form of power calculations, I guess. Yeah, and again, I don't know if that's what people do, but that's what I think would be normal. Because I would never change, depending on what you're trying to do, but generally speaking, I wouldn't change power. I'd change N, the number of participants. But then again, depending on your experimental design, maybe only collecting 20, collecting a maximum of 20 participants is like if you're working with a rare disease, right? If you're working with a rare disease and there's only like 20 in the entirety of New Zealand, then that might be the most rate limiting step, in which case then you'll have to change other parameters. So again, it's all based on your experimental design. Now, sample restrictions. Suppose that you feel practically you can only enroll 40 participants for your study. Oh, right. So for example, you're working with a rare disease and there's only 40 people, or let's say there are 100 people, but you feel you'll only be able to reach 40 of them. So that's why you put 40. You do not feel comfortable enrolling more than 40 due to various concerns such as time, practicality, eligible population, etc. As usual, you're expecting alpha equals 0.05 and power is 0.8. The effect size you're looking for is roughly a large effect size between 0.9 to 1.1. Now, running a participant through the placebo protocol costs roughly $800, but the attrition is 5%. Running a participant through the experimental protocol costs roughly $900, but the attrition is expected to be 20%. So this could be a drug study where when you actually give someone the actual drug, it could be that it's got pretty bad side effects and people drop out more. And so that's why if there's high attrition in an experimental group, oh, that's not good. So if you only had $38,000 in consumable money, identify number one, the best effect size detectable, and number two, the randomization weighting for the control and experimental group. And this bunch of code talks about this. So first of all, create a blank empty table, so ES effect size table, and you can see how we have experimental N is 30. If we had 38 people in the experimental group, but only 2 people in the control group, probably not a good design, but you can see how I've gone up in 2 all the way to 38. I've just, so remember you had 40 participants and you can basically control an experimental N should add up to 40, and you can see how it does. D in effect size, obviously we don't, it should be between 0, I think we need to calculate that, sorry. Alpha is 0.05, power is 0.8, and then cost will fill out. And so if you run this for loop, that you can read it in more detail, but essentially we create a table which looks like this, and then you can see the balance of participants in each group, and then followed by the minimum effect size you can detect. So if you had a awful experimental design of control N is 2 and experimental N was 38, the minimum effect size you could detect was only 2.09, which is a pretty big, so it's not a good experimental design. And that'd still cost you like 44,000, which is quite a lot. So if you had $38,000 in consumable money, identify the minimum effective thing. So it'd be somewhere around here. The minimum you could detect would be 0.95-ish or 0.93-ish, between 0.93 and 0.95. And the randomization weighting. So when you recruit a participant, you have to randomize him either into control or placebo. And then you can see, okay, you'll need 26 of them in the control group and 14 of them in the experimental group. So actually, if you ran a balanced control group, yes, you'd achieve the highest statistical power, but that would cost more money because potentially because the experimental group would have higher attrition, and so therefore it costs more money, yada, yada, yada. So yeah. So these are just example power calculations or ways to think through how you might design your power calculations. And I also include here just a list of other easy statistical power software. So whenever you're writing your own protocol, you might just go to, you don't need to use R. It's just easy. You can just go online, just do online power calculator. It's really not that difficult. As long as you have, what power you want, what N you want, and what effect size you want, it's very easy. Now, I will say, actually, more so the industry standard nowadays, or the more preferred software to run power calculations is G-Power, and it's free to use, and you can get it from, it's a German group that made it, and it's free to download and free to install. It's a GUI based, so it's a GUI based software. So you just click around, have some fun, but then it goes into much more complicated experimental designs. I, for one, like to keep things simple. That's why I've only had 2 groups and simple things that I can kind of understand, but that does go into if you had to run an ANOVA and how to convert F statistic into other things and all these other things, G-Power is very powerful for that. So yeah, but that brings me to the end of the course. That's what I'm talking about. Yeah, end of the course.